Well, now we're going to start Chapter 12, and Chapter 12 will actually be split up into two parts for us. The first, about 5 sections, will be covered in one unit, and then we'll have the remaining, plus some extras that are outside the book for the second unit. But this is on probability and statistics, so we'll have a couple of chapters or units on probability and statistics, and then a couple of units for the remainder of the term that will be on trigonometry. And starting out with just a couple of different ways that we display our data. We quite often will display our data in a frequency table. That makes sense. We will take something like, say I'm looking at what someone's favorite sport is. And I put the favorite sport here, and I might put the frequency here, and maybe football, basketball, etc., and put down what the totals are here. So we have the outcomes of the sample space. So the different sports that people like would be over in one column, and the number of times that they occur here. Now, sometimes we also talk about the relative frequency, and I should say something about that. It's not in the table, or in the note sheet, but relative frequency, let's say we knew we had a total of 100 people who were telling what the favorite sport was. And let's say that of those 100, and I actually should put that 100 over here. But let's say of the 100 people, let's say that 35 people said that their favorite sport was football. Well, then the frequency would be 35. The relative frequency would be 35 out of how many people were asked. So in this case, it would be 0.35. And let's say basketball, let's say there were only two favorite sports. Let's say basketball, we had 65 of the 100 people liked basketball. Then we would have the relative frequency of 0.65. And so the relative frequency will give the frequency in terms of either a decimal, fraction, or percent. It gives you the proportion of people who like that sport, as opposed to the frequency will tell you a raw number. You'll know how many people were actually surveyed and how many of those people were in each of the different categories. On the other hand, relative frequency, we actually would not know how many people were surveyed. We would just know what percent, what proportion, or what fraction of people liked that particular category. Now, cumulative probability would be where we are looking at accumulation, and we'll get to that more as we continue on, and I'll show you what I mean by that. And probability distributions are ways that we're going to show all the different events and the corresponding probabilities. And so if I only had two different favorite sports, I would be showing you the probability distribution for favorite sports, because I'm showing you all the different items in the sample space, or the ways it can come out, and the corresponding probabilities of each of them. And in a probability distribution, this has to be in terms of a probability, so it can't be raw number. All right, so let's get to a couple examples. So we have our first example, just as something real simple, and I have a frequency table, and we can see that the frequency table is talking about the number of people who are involved in at least one extracurricular activity. And so we can see that a total of 720 people were interviewed, and we can see what the totals are for the different categories. And all of these have to add up to 720 because you're either in more than one, or none. And so if we wanted to find using this frequency table, and it is a frequency table, it's not a probability distribution. A probability distribution would have these all as the probability of each of these events occurring. But if we want to find the probability that a student is involved in at least one extracurricular activity, let's show how we'll write that out. We want to find the probability of, and I'm going to let x stand for my variable of how many activities someone is involved in. So I want x to be greater than or equal to 1. And for probability, we always have to give it either as a decimal, as a fraction. If it's a fraction, reduce it, or as a percent. All of them are acceptable. If you're told to give one specific type, then do that. Otherwise, any of the three will be sufficient. And so if I want at least one activity, I know that here is more than one activity. Here is one activity. I would need the sum of those two. And these two add up to 504. out of a total of 720. Now, I would not leave the answer like that. I would need to either reduce it down as a fraction, give it as a decimal, it's 0.7, or I could say 70%. So again, this is a frequency table because it just shows the frequency of the occurrence of an object. Now, if I wanted to use the information from example 1 to find the probability that a student is involved in one or no activities, then I'm really answering the question. I want to find the probability that my number of people participating in an activity is less than or equal to 1, because 1 or none. So that would be our symbolic way of writing it. And once again, I'd have to add these two categories together. And these two add to 576 out of 720. And that's approximately 0.8, or I could say about 80%. So again, a reduced fraction, a decimal, or a percent. Now we're going to look at making up our own probability distribution from a specific situation. And so we have a probability distribution is going to be set up where we are supposing we have two spinners. We will assume that these spinners are fair, meaning that each of these outcomes 1 through 4 is equally likely. And we want to show the distribution, the probability distribution, for the sum of the numbers. And then we're going to graph our results. So we have, there's my first spinner, and again, we're going to assume the spinner is fair, so that each of these numbers is equally likely to come up when we spin. Move that up to the top. And here's my other spinner. Don't know why I made them smaller, but I did. And again, each of those numbers is going to be equally likely to occur, and the little spin tine is going to spin around and hit each spot evenly. And we want to look at what the sum is. Now, I'm going to make a little, kind of a little punnet square, and I'm going to look at the sum. And I know that here's my first spinner. Here's my first one, and it can come up 1, 2, 3, or 4. And my second spinner can come up any of the numbers 1, 2, 3, or 4. And so if I'm particularly looking at the sum of the two spinners being spun together, I don't care what the particular numbers are that come up. I just want to know what the sum of the numbers is. So the first spinner could come up a 1, and the second spinner could come up 1, and I'd have a sum of 2. I could have the first spinner come up 2, and this one a 1. And so on. 1 with 2. 1 with 3. 1 with 4. Okay. And there's the entire setup of the different ways that my situation can come up. So if I spin two spinners, those are the only different spins. The smallest sum I can get is 2, and the highest is 8. But I can see they're not equally likely. I have 4 times 4. I have 16 different cells here. So when I spin and I spin a sum of 2, that is the same likelihood as a sum of 8. Both of them come up 1 time out of 16. So if I'm going to show my probability distribution will show all the different ways that my situation can come out. And I'm going to let X stand for the sum of the numbers. And I know the smallest sum I can have is 2. I can have a sum of 3, 4, 5, 6, 7. Highest one is 8. And the probability of that, I don't want the frequency this time, I want the actual probability, and I will list it as a fraction. The probability is 1 out of 16. 3 occurs two different ways, a 2 with a 1, if there's a 2 on this spin and a 1 on that spin, or if there's a 1 on this spin and a 2 on that spinner. So I have two different ways for that to happen. Now I'm not going to reduce this in my probability distribution just so I can see my trend. I have 3 different ways for a sum of 4 to come up. I have 4 different ways for the sum of 5. I have 3 different ways for the sum of 6. 2 different ways for a sum of 7. And 1 way for a sum of 8. Now, you won't always have this symmetry in this type of a probability distribution, but again, it's called a probability distribution due to the fact that I have all the different outcomes in the sample space, it's called, the different ways that it can occur, and I have the corresponding probabilities of each of those. Now, I did say something about graphing them, and I'm going to graph a little histogram. A histogram is a bar graph where we have numerical values along this axis. And so I'm going to go along here. There's a sum of 2, there's a 4, there's a 6, there's an 8. Now, this might look a little bit different than the way you typically see it graphed. Here's 1, 2, 3, 4 sixteenths. There's 5 sixteenths. And this is my probability on this axis. Now, when I write my bar above 2, I'm going to do it the way a technology graph typically, or a calculator would graph. And I have this bar from 2 to 3. It has a probability of 1 16th. For the next one, it's 2 16th. For 4, which I'm going to put right here, that is 3 16ths. For 5, I have 4 16ths. And then for 6, I head back to 3 16ths, 7, 2 16ths, 8, 1 16th. And there's a little histogram, it's called, of my graph. Now, all graphs will not be symmetrical as this one is, but in this case, it does have that symmetrical pattern where it would kind of fold right here. Now let's flip over. Now, on the next side, we'd be looking at this rolling 2 fair six-sided dice. And I'm going to show you what the results are that you could produce on your own. In fact, we could turn the video off and you just produce it on your own. And I'm going to zoom in here. So when I had 2 fair six-sided dice, I took my first die and I wrote down all the different outcomes for the first die here. 1, 2, 3, 4, 5, 6, and a sum 1, 2, 3, 4, 5, 6 here. Now, you can see I did exactly the same thing that I did in the previous one. I just have more values in my cell. There are 6 ways for the first die to come up, 6 ways for the second die to come up. So there are 6 times 6, or 36 different outcomes within this matrix. Now, some of them are repetitive. However, they're all unique rolls. For instance, if I go to these 7s, this roll and this roll are different rolls. This one, the first die came up a 6 and the second die came up 1, versus here, the first die came up a 1 and the second die came up 6. They just happen to result in the same sum, but they are different rolls. And so when I go through and design my probability distribution for this one, my sums can be as small as 2 and as big as 12. And I do have that similar pattern that I had before, that the sum of 2 and the sum of 12 have the same probability. But I have my probability distribution. I have my random variable axis standing for all the different sums that my 2 dice can have, and the corresponding probability of each. And if I graph this graph, it will produce a similar symmetrical graph as our previous page. Now let's look at simulating. And so right now you did, I believe, a little bit of simulation in Algebra 2, but let's look at this next question. Let me zoom out a little bit. And we want to use the random number generator on our calculator to simulate rolling 2 dice. So I'm going to do that. And let's see. I'm going to go to Math, and I'm going to go over to Probability. I'm going to arrow back, actually. And I want random integer. And now I'm going to hit 1, 6, 2. That will produce random numbers that are from 1 to 6. Whoops, and I see I didn't hit random integer, did I? Let's go back. We'll clear that out. Math, probability, and number 5. There we go. That looks better. 1, 6, 2. And now this is going to produce random integers from 1 to 6. and it was going to give me two of them. And so I want to use the random number generator to simulate rolling two dice. And so I did that. If I do it right now, I can see, oh, my first sum would be 8. My next sum would be 6. My next sum would be 6. My next sum is 4. Next sum is 7. Next sum is 5, etc. And there are a lot of ways that this sum can come up, anywhere from 2 to 12. So, well, to turn off the video and do that and make a little tick mark chart like I did. I put down my, there we go. It's kind of getting a little glary here. But I put down a frequency distribution, not a probability distribution, a frequency distribution of rolls of 2 all the way up to rolls of 12. And in my display, when I did it one time, you can see what my results came out to be. I only got a sum of 2 once. I never got a sum of 12. I didn't get a sum of 10 either, but I only did this with 20 trials. So I had to hit that button 20 times. Now, in the end, I could change this into experimental probability, and I could say out of 20, I got this happening 1 out of 20 times. I got this happening 1 out of 20 times. I got this happening 2 out of 20 times, etc. And if I continue to hit that button over and over and sit here all day, my theoretical probability, which is up here, would end up being my experimental values would end up being very close to this. But I may have to do thousands and thousands of trials to get that to happen. So we do have to remember that when we are simulating and we don't do a lot of trials, 20 might feel like a lot, but relatively speaking, it's not very many, that when we do trials, we end up getting approximations for probabilities once we turn the frequency into experimental probability, and we're trying to get this theoretical probability. Now, this last one we're going to look at is another way of doing a simulation, and you will be responsible for doing some simulations. And we have a situation that at a library desk, we know how many calls, C, are made during a particular hour. And so we know that they receive C calls each hour. Apparently, they never receive more than 5 calls. And the likelihood of receiving no calls is 5%, 1 call 15%, and etc. So the most frequent thing that happens is for them to have 3 calls within a 1-hour period. Now, we want to run a simulation, and notice that the likelihood of each of these numbers is not the same. So I can't do this. I can't go over here on my calculator and go, hey, I'm going to simulate getting numbers from 0 to 5. If I do this and I go math, probability, my random int, and I do 0, 5 and go, I got this down. Just do that, and that's going to simulate how many calls were made. That won't work because this assumes that 0 through 5 are equally likely going to occur. And we actually know that the likelihood changes depending on which value you have. And 3 should come up more than any other number. 2 should come up in the next likelihood. And 0 and 5 should only happen about 5 out of 100 times. So we actually have to set this up with a little different assignment. And if you'll notice, my probabilities are, this is 5 out of 100, 15 out of 100, 25 out of 100, 30 out of 100, 20 out of 100, 5 out of 100. I need to generate 100 random numbers. And I need 5 of those random numbers to stand for getting 5. I need 20 of the random numbers to stand for a 4, and etc. So I look at what my probabilities are as far as the decimal, and I can see I need the 10th, 100th place. I need to generate 100 numbers. And so here is my assignment. Now, this is not the only way to assign them, but I did the following. I'm assigning a digit of 0, and these are the only numbers that I need to generate, 0 through 5. And I'm going to let the first 5 numbers, because the probability is 5%, 5 out of 100, I'm going to let the first 5 numbers stand for, you got a 0. No one called. And then the next 15 numbers, I'm going to let stand for a 1. And so 6 through 20, I can see is not shown up too well. But I will write over it with a pen, and then it will show up better. So I have 1 through 5 is my 0. I'm letting 6 through 20, which is 15 numbers, stand for a 1. Now I need 25 numbers to stand for a 2. So I'm going to let 21 through 45 stand for a 2. Then I need to let the next 30 numbers stand for a 3, and that will be 46 through 75. Then I need my next 20 numbers to be a 4. And then my last 5 numbers, from 96 to 100, if you count those on your fingers, that will be 5 numbers. Those need to stand for a 5. So now I will have each of the numbers equally represented. So if I did that simulation right here, and I went back, and I'm just going to do a little second entry and change that, generating 1 to 100, we had to figure out in an 8-hour period how many, so use the random numbers to predict the number of calls received during an 8-hour shift. All right, so we'll do this one. I'm going to put this on this little sticky note. So the first time I just got a 28. Well, I need to look at mine and say, what's a 28? A 28 means 2 people called. So the first time, 2 people called. I got a 28, and that is 2 people called. Hit the button again. I just got 90. 90 stands for 4 people called. Hit the button again. 20. 20 stands for 1 person called. So I do it again. 53. This is my 4th hour. 53. 3 people called. Got 33 next. 33, that stands for 2 people called. 71. 71 stands for 3 people called. I'm in my 1st, 2nd, 3rd, 4th, 5th, 6th hour. Got 2 more hours to work with. Hit the button again. 97. That stands for 5 people called. Busy during that hour. And last hour, 93. Oh boy, people are calling at the end of the day. Got 4 people called. So if I wanted to find out the total number of people that called on this shift, I'd have 6, 7, 10, 15, 24. 24 people called. 24 people called in that 8-hour shift because I have to do each hour separately. Now you're ready to practice.